In my last video, I talked about the relationships within the ideal gas law. Go ahead and click the link if you haven't already seen that. What I did not cover in my last video is that the ideal gas law is not actually the real world. Instead, it is a model that tries to represent the real world with pretty simple math, and it does so accurately for the range of conditions we normally deal with. But like most models that we use to represent the real world, there are times when it is no longer accurate to use the ideal gas law model. And in order to understand those times, we need to first talk about the assumptions we used as building blocks to create our model. The first assumption is that the volume of our container is much larger than the volume of our particles. So we can ignore the volume they individually take up and instead treat particles as points in space with no dimensions, meaning particle volume is negligible. The second assumption is that the control volume we are looking at has a statistically large number of particles. This means we can ignore the individual behavior of particles and instead look at the sum behavior as a property of the gas. This only works if we have a significant number of particles. Our third assumption is that the only forces acting on particles are caused by elastic collisions. Elastic meaning that kinetic energy is conserved through a collision, so the velocity of particles before and after collisions are equal. This most notably will be ignoring the effects of van der Waals forces, which is an attractive force between all particles. We can ignore it because the forces from collisions are typically significantly larger than that of van der Waals. In summary, we are assuming that our only forces are from elastic collisions. Our last assumption is that the temperature of the gas is directly proportional to the linear kinetic energy of the individual particles. This will be treating it as if all the energy gained by heating will go into the linear velocity of the particles, and we'll be ignoring any effect temperature has on the rotational energy of the particles. Last assumption is temperature is proportional to kinetic energy. So when does ideal gas law become inaccurate? Well, that is when the assumptions we made no longer make sense for our given conditions, such as when gases are at really high pressures. At high pressures, the gas particles are so close together that we can no longer ignore their volume relative to the container. The number of collisions will be dependent on the size each particle takes up. At lower temperatures, the forces from collisions are smaller due to the lower velocity of particles. This means that van der Waals forces will have a greater proportional effect on moving particles. If the particles are at a low enough temperature, we will no longer be able to assume that van der Waals forces can be ignored, meaning our third assumption is invalid. There is actually a property that describes how ideal a gas is at a given set of measurements, and that is compressibility. Perfectly ideal gases will have a compressibility factor of 1, and looking at the equation, this makes a lot of sense, since it is just the ideal gas law rearranged. Ideal gas law is pretty accurate for the conditions of gases that we'd normally deal with. As you can see on the graph, when we are at about room temperature, the ideal gas law is pretty close to the behavior of standard air. However, when we look at the lower temperatures at high pressure, we start to see a substantial drift away from ideal behavior. This is why it is important, when using any equation or model, to keep in mind the assumptions used in your tool. I hope you enjoyed the video, and stay tuned for more to come from this channel.